Welcome back. Let's see now how to extend that flatland 2D version of formulating lighting estimation into 3D. Okay, well, it's going to turn out there's some good news here. Good news and bad news. The good news is same equation works. Whether you're 2D, 3 doesn't matter. So let's take a sphere right here. You can see that it seems to be being illuminated from somewhere up there. This little part is brighter. This part is in shadow down here. And let's see, the brightness at any one of these little patches is equal to its surface normal, well, that's what these little hairs coming out of here are, times a dot product with the light direction, that's just some vector in 3 space, and the ambient is still an ambient, just some scalar values. So what's the surface normal on a sphere? Well, the surface normal on a circle is you draw a little tangent line, and then you take perpendicular to that. And for a sphere, you draw a tangent plane. Yeah, so take a little tiny plane, something like what you see in these little tessellations here. And now once you have a plane, I can draw a vertical vector coming out, and that's the surface normal. Okay, so turns out, infinite light source, Lambertian surface, it reflects light equally, it's not a shiny, it's a matte or flat surface. The same model holds, and again, I don't care about the color of the sphere because I'm only going to estimate that vector up to a scale factor because the light is infinitely far away. Okay, so that's the good news. Now let's just write it out and make sure we see all the linear algebra here. So first of all, this is now a 3 vector. So nx, ny, lz. The light is a 3 vector, of course, lx, ly, lz. So when I write out this equation for one point on the surface, I get b1 is equal, pick any one of these surface patches, I don't care, is equal to the x component of the surface normal times the x component of the light, y, z, plus the ambient term. Notice that this is linear. What is unknown? Lx, Ly, Lz, and the ambient term right there. And of course, all of those unknowns are being multiplied by a known value, in this case the surface normal, or just the constant 1. Okay, so now I've got 4 unknowns, Lx, Ly, Lz, and A. As promised, 4. So if I get the surface normals and the brightnesses at 4 points on that sphere, I've got a fully constrained system of linear equations. Look, everything looks perfect. The only difference, by the way, is notice that if I cross out that row right there and I cross out the z component, I'm back to where I was in 2D. So the only thing I had to do was add in this, and because I added an unknown, I had to add in another row right here. Okay, good. So what's known? That's known. Of course, the x, y, and z component of the surface normals are known. And the Lx, Ly, Lz, which are constant across all 4 equations, and the ambient, constant across all 4 equations, are unknown. Good. 4 equations, 4 unknowns, should be a piece of cake. So let's go ahead and write it out. So I've got this vector right here, b1, b2, b3, b4, 4 points on the surface. 4 surface normals, x, y, and z. And then a vector of 1s times the ambient Lz, Ly, Lx. Exactly like before, we just have 1 extra row, and this part is new, this Lz component. All right, this looks awfully linear, and now we know what to do. Let's get it into matrix form. So I'm going to take that equation right there, and I'm going to put, obviously this vector stays the same. I've got nx1, ny1, and z1, 1 times Lx, Ly, Lz, A. That's my unknown vector. This is my known matrix. I can now start to fill in all the rows corresponding to each row over here. And now what do I have? I've got a known vector. I've got a known matrix of size 4 by 4 square matrix. As long as these surface normals are not collinear, I can invert that matrix and I can solve for the 3D light direction and the ambient term. We know how to do this. We're going to turn the crank. Vector B is equal to matrix n times unknown u. Left multiply both sides by the matrix inverse. Matrix inverse times matrix, whether it's 4D, 3D, or 2D, is equal to the identity. And now we have the unknown, which is the matrix inverse times B. So invert that. So pack in a bunch of surface normals, invert it, multiply. Okay, so the good news is that that equation works in 2D and 3D. And really, we didn't have to do much more work. All we had to do is build a 4 by 4 matrix instead of a 3 by 3 and add 1 more row to the system. Not very demanding. Okay? So what's the bad news? The bad news is, how do you get 3D surface normals when you have a flat image? right? So when we were working with the circle, I just needed the tangent. I needed to fit a line and get the surface normal. That's trivial to do. I can do that in the image. But when I give you an image of a sphere, you've lost a dimension. It's a flat image. I don't have that third dimension. Now, if I know it's a sphere, maybe I can figure out the surface normal, but I've lost a lot of information. And so now the difficulty, this is the bad news part of the story when we go from 2D to 3D, is how do you get those 3D surface normals? Now, I can give a whole nother lecture about this, and I'm not going to do it, but there's some really beautiful work from the computer vision and computer graphics community on estimating 3D models, in particular of people's faces. And the reason why, by the way, just for intuition that this works for faces is that the geometry of faces is fairly regular. It's symmetric. Most of us have fairly similar looking faces. I mean, we obviously look very different, but the geometry, we have a nose, we have eyes, we have a forehead, we have cheeks, we have a chin. And so things are fairly regular. And it turns out that because of that, and because the image, in fact, captures quite a bit of that information, we can build 3D models from faces. And I won't go into how that works, but we can take a single image, sometimes multiple images of a person, and we can automatically build 3D models. Once I have that 3D model, I've got surface normals, because now I've got 3D. I can go in and look at any one of those patches, draw a little vector perpendicular to that patch, and so I have to do a little bit of work to get 3D models, particularly to analyze humans. Now, because we only want to, so now what we're going to do is we're going to take that 3D model, we're going to superimpose it on top of the captured image. Why? Well, what do I need to estimate light direction? I need to know the brightness, what is my color, and what is the 3D normal at that point. So I have to overlay the 3D model, I get the normal, with the surface, I get the brightness. The brightness is on the left-hand side of the equation, the surface normal is on the right-hand side of the equation. That's another problem you have to solve, an alignment or registration problem. I won't get into that, but we can solve that problem as well. I'm going to carve out things like the eyes and the hairs and the ears because I want everything to have the same overall reflectance. That was the assumption that the appearance of everything is exactly the same. And once I've solved those two problems, now I can go in and analyze the original image that we started with. So what we're going to do is we're going to build 3D models for the 7 people that you see here. And again, I haven't described exactly how to do that, but we know how to do it. We're going to align those 3D models to each person's face. And we're going to estimate for each individual, where is the light? Now, this is taken outdoors. And so if it's taken outdoors, the light should be in the same place for everybody here. On the other hand, if the North Korean leader was photographed elsewhere earlier in the week, month, or year, and then digitally inserted here, well, something's probably going to be wrong because it's unlikely that the sun in this photo and in the original photo are exactly the same. All right, so that's what we did. So we built a 3D model for Kim Jong-il. Here's what you can see as I rotate his face. You can see his model. I've superimposed that on top of the image that you just saw earlier, and I'm going to estimate his light, and I'm going to do that for the people around him as well. And now what I'm going to do is I'm going to render a sphere on top of each individual, and that sphere is illuminated with the estimated light direction for each individual. And we did that just so we can visualize what the light looks like. And you can see it's pretty consistent. You can see that the light is, within a couple of degrees, more or less exactly the same. Yeah? And so we hypothesized that, that the claims that the lighting on this image were wrong is simply incorrect. We think what was happening with the shadow is that Kim Jong-il was standing slightly more forward, and that caused the shadow to be shorter. And it turns out that that missing horizontal line was because where he was standing there is a door, and that little panel moves, and then there's a stairwell that goes up into the stadium, and that explains that. And by the way, we were pretty sure that he wasn't dead because a couple weeks later we found out that he in fact was still alive. He obviously died a little bit after that. But this was a really interesting example of how very simple linear systems can be used to formulate what would appear to be a fairly complex problem. And of course we had to make some assumptions. We had to assume certain things about the surfaces. We had to assume certain things about the lighting. That's always the case. And notice there is sort of the power of formulating a problem within a linear system. Once we wrote out that equation, and once it became linear, trivial to solve. You just turn that crank, build the matrix, invert the matrix, and you can get an estimate of the lighting, of ballistic trajectory, and many other things with even just these very simple linear systems. And that's really exciting and very powerful. Now, one of the drawbacks of everything we've done up until now, both for the ballistic motion and for the lighting, is we had exactly perfectly constrained system. So 4 equations, 4 unknowns, 3 equations, 3 unknowns, 2 equations, 2 unknowns. But in the reality, in that image and in the earlier one of ballistic, you have a lot more constraints. So for the lighting, I've got every little patch on the face is a constraint. For the ballistic motion, every single point where I can measure the ball is a constraint. Why aren't I taking advantage of that? I mean, if I have a noisy system and there's a little bit of error, surely having more measurements is going to be better for me. I want to be able to take advantage of that. I want to be able to take advantage of every measurement I make, even if it's way more than the parameters I have to estimate, because it's going to give me robustness. And that is what we're going to do next. So we're going to talk about what happens when you have more constraints than you do unknowns. You don't just pick as many as you need, the bare minimum. You want to take advantage of all of them. And you can take advantage of all of them in very different ways. And that's what the rest of the class is going to be about. All right, we'll pick it up there when we start the next lecture. See you then.